Next, I would like to talk about floating node method. I developed this method during my PhD and postdoc. The essential idea is in the definition of the element. Previously, we have presented that the element has always been defined as a selection of nodes, and we have always attributed degree of freedoms to the nodes. But if you think about our earliest geometry classes, we always describe a rectangle by saying that it has 4 nodes and 4 edges. So in this case, the reason why in the finite element method we never considered edges is that we started off with the assumption that the material would behave in a continuous manner, and hence we can use continuous interpolation functions between the nodes, and we never needed to consider the edges. But now with fracture, most of the time, a crack would propagate across the edges. It would cut across some of these edges, and then you are introducing additional crack nodes on these edges, and numerically you are introducing additional degree of freedoms there. So at this moment, your previous fundamental assumption that the element behaves continuously throughout the analysis is no longer valid. And hence I took the departing idea that the element is essentially composed of nodes and edges, and these edges would have orientations. So I give a convention like this, and then I attributed the degree of freedoms to both nodes and edges. So in the definition of the element, if you were to have a comparable input file, an element would have nodal connectivities and also edge connectivities, and you would then have corresponding degree of freedoms to both nodes and edges. And here, for instance, I could allocate a pair of degree of freedoms to each edge. When a crack appears, I could activate the degree of freedoms associated with the cracked edges to directly partition this element into 2 sub-elements. And note that these 2 sub-elements, they have everything defined. Once you have your crack appearing in the element based on your failure criteria or propagation criteria, you would then be able to calculate the locations of these crack nodes. Now you have the degree of freedoms already allocated to these edges. You can use these degree of freedoms to represent the displacements of these crack nodes. Hence, you could directly form the 2 sub-elements, and note that they are standard fully integrated sub-elements. So that's not the case with the phantom node method or XFEM. And when you want to describe the displacement field in this element, you simply write just a control parameter. So if your x lies within omega A, you have the displacement field of sub-element 1 to represent this displacement, and then if your x belongs to omega B, similarly you have the sub-element 2 displacement field. Each of these sub-element displacement field can be obtained by a straightforward standard finite element interpolation using the standard finite element shape functions for the respective sub-elements. With this method, we have a very flexible way of defining elements. So this is just a case for modeling a single crack across the domain. We could, of course, form a cohesive element in between. Now we have the crack nodes defined, we have the degree of freedoms available, we have everything that we need to define the cohesive element in between. And we can also only activate 1 degree of freedom set on this edge to form just a weak discontinuity, which is usually a bimaterial interface. So imagine this omega A has material A and omega B has material B. Here you would have a continuity in terms of displacement. So you have sharing degree of freedoms here, but discontinuous in terms of strength field because you have a different Young's modulus. So this is entirely possible and is very straightforward. However, this is not so straightforward in the case of phantom node or XFEM. And also you can make use of, so you can design your element to model these kind of more complex crack patterns. It's a matter of how you implement your control statement. So you could really creatively activate and deactivate the degree of freedoms within your element to make the crack propagate in a very complex manner. And if you further extrapolate, you could think the element of being multi-purpose. You have a global mesh, and every element is defined with a pre-allocated degree of freedoms on the edges and also within the domain of the element. To be completely generic, this element could take either of these different rows, and it could change between the rows, and that is only a matter of integration, how you integrate. So here you would have 3 integration domains, and here you would have 4, and it's your choice to subdivide your original domain into different sub-elements. And as long as the solver is concerned, the solver is only seeing this big element. So this is a flexible way, and we can further extend it to 3-dimensional case. Here we would then include in the definition of an element both nodes, edges, and also surfaces. These surfaces would also have orientation. For instance, you can design orientation in the usual convention with outward normal. And then we can allocate degree of freedoms on all these geometric entities. So you would have nodal degree of freedoms, edge degree of freedoms, surface degree of freedoms, and volumic degree of freedoms. And you can make use of these pre-allocated degree of freedoms to tailor your element to a specific application. So that depends on the characteristics of your material and whether you expect to have a T-crack junction or some channeling cracks intersecting each other, then it's up to you. And here I'm going to demonstrate the application of this method in a composite laminate, where I expect to have different orientations of matrix cracks on top and bottom plies. Here I would have the horizontal edges allocated with floating degree of freedoms. I have also a cohesive interface element enriched with additional degree of freedoms on the edges to be compatible with the top and bottom plies. And I could automate this process such that on the global mesh, it's a planar mesh, no feature along the thickness direction, and then the layup becomes the definition of the element. Every time I want to change a different layup, I simply generate, according to an automated algorithm, a different definition of the element. So this will be a big 3-dimensional floating node element with all the features included in terms of integration. And the solver, the overall system level, only sees this big element, and the user knows exactly which configuration it is corresponding to in terms of a layup. Using this element, you could then be able to represent this kind of crack networks within the element. So you have a typical staircase patterns in the case of open hole tension, where you have matrix cracks and delamination, and then the delamination propagates again into matrix crack, and then again becoming delamination. So this gradually reaching a zero ply where the crack cannot cut across the zero ply that easily, and then it deflects into a delamination. So here you can see that the cracks propagate along the correct orientation, which are the fiber orientations.